Welcome, ladies and gentlemen, to our Reflect webinar on efficiency in geothermal operations and virtual visit to Insheim. My name is Katrin Kieling, and I'm working at the Helmholtz Center Potsdam, GFZ, the German Research Center for Geosciences, and I'm the project manager of the Reflect project, which is a Horizon 2020 project on redefining geothermal fluid properties at extreme conditions to optimize future geothermal energy extraction. In this project, I have the pleasure to work together with a number of outstanding researchers, actually from 10 different European countries, who are committed to close gaps in the database and also in the basic understanding of chemical and physical properties of geothermal fluids, such that we can avoid unwanted processes during the geothermal operation and adapt also the operation and the plant layout to those challenges. Today, we would like to focus on the first results from the Reflect project, which are connected to the investigations performed at the Insheim site. And I have the pleasure to welcome two of our Reflect partners in this webinar. We will start the presentation with the coordinator of the Reflect project, Simona Regenspurg from GFZ Potsdam, who will present the general Reflect project and also its approaches to improve efficiency of geothermal power plants. And then this will be followed by a presentation by Joerg Uhde on the efficiency of geothermal operations, and then the virtual visit to the Insheim geothermal power plant. Each of these presentations will be followed by a 5 to 10 minutes question and answer sessions. And for that, please type your questions in the chat, and I will read them then out to the presenters. I encourage you to already write the questions during the presentations, such that we can directly attend them after the presentation. And then I have a very last remark before we start. This webinar will actually be recorded, and my colleagues Alberto Sanchez and Maria Lopez from the European Federation of Geologists, who have organized and set up this webinar, will publish the recorded webinar on YouTube afterwards. Having said that, we will now start with the first presentation by Simona Regensburg, and I quickly introduce Simona. So Simona Regensburg is working as a research associate at Helmholtz Center Potsdam, German Research Center for Geosciences, in the section Geoenergy since 2009. She is the head of the working group Geothermal Fluids, and the focus of her research is on the study of geochemical processes that take place during the operation of geothermal power plants. These include reactions under increased pressure and temperature conditions, interactions between water and rock, and their effects on the environment. Simona Regensburg studied geology and hydrogeology at the Ludwig-Maximilian University in Munich, Germany, and completed research stays in the US, Sweden, and Switzerland. And finally, she's habilitated at the University of Berlin. And currently, she's of course also the coordinator of the Reflect project and the scientific head of the project. And thanks to her initiative, we have now the possibility to work on chemical and physical properties and to bring the research to the next level. And with that, I would like to hand over to Simona. The floor is yours.
So, good afternoon, everybody. Thanks a lot for your nice introduction, Katrin. I'm very happy to present to you today the Reflect project, give you a little bit of an introduction of what we are doing in Reflect, and a little bit a glimpse on what we did so far at the Insheim site. And then I'm sure that you're very curious to see the Insheim and more information about the good geothermal, successful geothermal site in Insheim. So the Reflect project, Katrin already read the complicated title on redefining geothermal fluid properties at extreme conditions. So that is actually the key word, that we look at the extreme conditions of geothermal fluids and try to understand the fluid at extreme conditions. Yes, we are 14 partners coming from all over Europe who are contributing in this project. This project started in January 2020. So we are still in the middle of collecting data and interpreting them. That's why we have not yet, of course, final results, but a little bit we can already present to you. Yeah, so what is the background? The background of the project is that many geothermal operators suffer problems that are related to scaling and corrosion. Scaling and corrosion examples you see here in the pictures. So scaling the precipitation of minerals that clogs pores of the reservoir, or the tubes and pipes of the geothermal plant. And this leads to often to downtime and high maintenance costs, and even failure of geothermal installations. And they are sort of related to unknown properties of the fluid, because if the fluid properties would have been better known, one could model these reactions and predict them, and that by that avoid them. And the attempt of Reflect is to understand these unknown fluid properties better. And to show you these, what is not known about the fluid properties of geothermal fluids, that is given here on the left picture. You see a temperature salinity diagram, and in blue the areas where most geothermal fluids plot in here in temperature and salinity. And that also explains the term of extreme, because extreme means we have either very high temperatures in the geothermal fluids up to 300-400 degrees C, or very high salinity fluids up to several hundred grams per liter salt content. And that makes it really difficult to predict chemical reactions. So the dashed areas give you the areas that are not well understood in geothermal fluids. For the high temperature fluids, these are, for example, the kinetics and processes of polymerization and precipitation of silica. Which presents often a problem in the in the high temperature fluids. The purple area is data on mineral solubility, pizza coefficients, and fluid physical properties. That is especially for the highly saline fluids a problem. The gassing reactions are not well known in the whole range, and in the lower temperature range but high salinity range, the relevance of microorganisms and organics, it's hardly understood at all. So that is the attempt now of Reflect to get to have a fundamental approach and understand these, get an insight, a better insight into these dashed areas of this diagram. The objective is to do in the end accurate predictions by thorough knowledge of the physical and chemical properties of the geothermal fluids. Our slogan or the concept is from react to reflect. So instead of just reacting to a problem that already exists, we want to reflect first by understanding the fluid properties and by that avoiding the problems from the very beginning. We have 7 specific goals in Reflect, and related to these goals is our project structure. We either focus on the hot fluids or on the highly saline fluid, that both have a little bit of different challenges to master. Most of these of our goals are related to data generation, and so these are the first 2 work packages, and the work package 3 and 4 are more on data application, by using this data either for system modeling or by a fluid atlas. So these goals we have is to extend databases for mineral precipitation to higher temperatures and higher salinities, to determine the extent and location of the degasification front of geothermal fluids, to determine type of organic matter and microorganism in the fluids, determine the fluid physical properties. Also, we want to develop a downhole sampling technique for hot and super hot systems. And as I said, for the data application, we want to verify the data sets that we obtain for reactive transport modeling and for setting up a geothermal fluid atlas. So the first task in both work packages is about characterizing natural geothermal fluids. We have a range of geothermal sites where we look at These are either the highly saline sites, high temperature sites, or some sites that are a little bit of both. And at all these sites, we did collect samples and did a very intensely data analysis. So one of these sites is the Insheim site, where we will go a little bit deeper today into the results. What we analyze is, as I said, a range of parameters, the physical chemical parameters, if possible, all relevant cations and anions, a range of isotopes, the gases in the fluids, if available, the scales, doing chemical analysis and mineralogy of the scales, determine if and what type of organics and microorganisms is in these samples, and also radionuclides in fluids and scales are analyzed. So now let's go to Insheim. The site Insheim is in the southwest of Germany. I'm sure you will get better pictures of the site later on by Joerg Uhde. Some facts in the beginning. The site is in operation since 2012. The temperature, its production site is 160 degrees C, and it's injected with 65 degrees C. It produces 50 to 80 liters per second, and the fluid is used to generate electricity. The well depths are around 3,800 meters, and they encounter muschelkalk and sandstone rocks. Salinity is quite high, it's around 100 grams per liter. And they used to have problems with barite and lead precipitates, but apply inhibitor since a while quite successfully. In Reflect, the Insheim site is involved in a couple of topics that we investigate. First, it is part of the, it contributes to the database and to the fluid atlas. Here I will not show much data because the fluid atlas will be shown in a different webinar in the beginning of next year. What we did was on-site experiments on silica precipitation. We did an intense organic and microorganisms analysis. And Insheim is also the site for reactive transport modeling verification, but here also the results are still in progress and will be available only at the end of the project. So I just can give you very, very first ideas about what we found out in Insheim. So just to show you how in general our database in Reflect looks like, that's for all the fluids that we analyze. We have templates that include many parameters, and we try in Reflect to fill out these templates in as much detail as possible. So this was done by our project partner Hydroisotope for the Insheim sites. We have most of the data. I will not show you that now in detail. So we have analyzed basically the fluid and the gases in the fluid, including some of the isotopes. So what we did on site last year was to do a little in situ silica precipitation experiment. The background for this experiment was that although the fluid is currently injected with 65 degrees C, that there was the consideration to use the fluid also for greenhouse heating and cool it further down. And then it might be that silica would be highly oversaturated in that case and precipitate. So silica precipitation is a big problem in many geothermal sites, because what you see here on the left picture down here, most reservoirs are silica based, and with increasing temperature, more silica would be dissolved in the fluid. So if you have a high temperature in the fluid, it also contains a lot of silica, and if you cool down the fluid, it precipitates. Problem is, one never knows exactly how fast it goes and where it happens, but it can clog the pipes of the geothermal plant, or also the pores in a reservoir, and that's something the operators of course do not want. And that's why we did that experiment, in order to find out if, because we would have a high silica concentration, if it would be further cooled down, we wanted to know if it precipitates. And that's something one can of course simulate in a lab experiment, but you will never get all the parameters together in the lab experiment that you have in the field. And that's why we did a rather short experiment that tried to give us at least an idea what could happen in terms of silica precipitation at the site. So what we did is that we took fluid from the injection site and either decreased the pressure or the temperature down to 30 degrees C and decreased either the pressure to 1 bar or kept the pressure at 20 bar. And then so this affords a bit complicated setup to keep the pressure that high. For that we have our fluid monitoring system that you see here on the right that has a special sample holder from beer, and it allows to hold the pressure at these high pressure of 20 bars. And we could also collect samples over time and see if silica would precipitate over time from the fluid. And what we found actually was shown here. So we analyzed directly in the field also silica by photometer, and we found that if we keep the pressure at 20 bars, the solution was clear in the end, and there was no clear sign of silica precipitation. Also in the beginning, it was like the black line you see here, it decreased a little bit, but maybe this is also just a measurement error. On the other hand, if we decrease the pressure independently of the temperature, we saw that the solution was getting cloudy, so probably silica precipitated, and also silica concentration like decreased, like you see here on the blue line. So apparently the pressure rising is keeping the pressure is very important for keeping silica solutions more stable. That was what we found out here. The results on organic analysis are shown here. What we did was our PhD student Alessio Lines did actually was to analyze the DOC, the dissolved organic carbon content of the production and its injection site. And one sees that at the injection sites, it is much higher, with 12 to 15 milligram carbon per liter. And that is because an organic inhibitor is added to the fluid that consists of mainly of organic components. The composition of the inhibitor is shown on the diagram at the bottom. It consists mainly out of low molecular weight acids. And then you see the composition of the fluids at the production and at the injection site in filtered and unfiltered samples next to it. And you see, interestingly, that that here the composition is mainly low molecular weight neutral components. And so what one sees is that the inhibitor apparently reacts very quickly with the fluid and turns from an acid to an organic neutral. So this is kind of interesting. And even without the inhibitor, the organics that we have, which is in general pretty low, actually consists also out of these low molecular weight neutrals, which is actually to be expected in these high temperature fluids that we have at the Insheim site. Finally, I come to the results of microbiology. That's always very impressive to observe our colleagues from Neuchâtel in the field when they collect samples for microbial analysis, because they have to filter a lot of fluid in order to enrich their cultures. So you see them here at work, and the filter residues that they obtained from the filtering. A field experiment they did directly in field was to add the fluid to the so-called Vinogradsky columns, where some sort of medium that allows bacteria or microorganisms to grow was directly added. And these columns, so I will not show much more results because they are still not finished, but one saw in these columns after a short time already in some of them, microbia grow by formation of gases and also precipitation of some sort. Let's put it this way. So what the microbiologists mainly do for their molecular methods is, so first they get the large amounts of samples, they filter it to concentrate the biomass, and then they do DNA extraction from the cells, do the sequencing from there, and analyze these data to determine what type of microorganisms or fungi are actually in these samples. For the DNA extraction, they use two different methods actually. First, in one step they do just a pure DNA extraction, and as the second step they separate the spores and analyze them separately. And that is quite interesting because it gives a little bit of different results. What you see here on the right diagram, the red areas give you the phyla, so the type of microorganisms that were directly analyzed. Green, those with the spores, and sometimes they give different results, and that's why it's important to compare both results and for the interpretation. You see definitely that there are a lot of different microorganisms were identified. What the colleagues then also did was to isolate the cultures. So you see here under the microscope a bacterial isolate from Insheim. So these little worm-like things with a length of about 10 micrometers. These are bacteria, and from the liquid cultures, they were isolated at 60 degrees C, and they grew quite well. Also then on solid media, so these grown microorganisms were further investigated, like what you see here on a scanning electron microscope picture. It's the same organism of filamentous spore-forming bacteria. So it's I think a very nice picture, shows you how many of them are in this culture, and this one grows pretty well between 40 and 75 degrees C, not at colder temperatures, and the pH range where it grows well is 6 to 9, and not at pH 4. Yeah, so these are also first results from the microbacterial analysis. Further characterization is ongoing. It's quite interesting actually that we found at these conditions that we have in Insheim so much life. So that is already a big result, I think. And with that, I stop my presentation. I want to thank the Reflect team that most of the time was just meeting and virtually. We had one kickoff meeting, but hopefully it will continue. I think also if you have questions on the microbiology, that Dana Brenja has joined this meeting, maybe she can answer better questions on the chat on the microbiology. And with that, I want to thank you for your attention, and I'm curious to your questions.
Thank you very much, Simona, for this very nice presentation. We already have a first question in the chat on the bacteria. Are the bacteria coming from the reservoir or from the surface?
Well, they were collected at the production site of the well, and everything was sterile. So the way these microbiologists work is that they are pretty sure that they do not contaminate somehow from the surface anything. So, and the fluid was produced for a long time before getting the samples. So one can be pretty sure, I think, with that it comes from the reservoir.
Okay, thanks a lot. We actually have immediately a second question, which is a bit more in detail. Are the bacteria encapsulated in the formation water dating from Triassic ages or later coming from surface infiltrated waters?
So that's a good one. Well, I think that can be answered if isotope analyses from the water are done, and I think they are done, that the water is actually from the depths, that there is no younger fluid entering. Probably, I don't know if Joerg Uhde later can say anything about that, but so far as I know, the fluid comes from Triassic age, so there should not be any younger fluid infiltrating here. But of course, if yes, it should be investigated if these fluids have that age. So that's a very interesting question. And yes, maybe also I think Pilar just wrote in the chat that she might be able to answer some questions here on the microbiology.
Pilar, there she is. Pilar, I think you can unmute now and answer.
Okay, so I am on mute now?
Yes.
Yeah, so what we think for this particular bacterium, as Simona mentioned, is it is an spore-forming bacterium, and spores are dormant structures, and they are known to withstand in this dormant state for very long times. So there is a possibility that they are indeed extremely old organisms that you reactivate when you create conditions that allow them to regrow. So we are investigating that, and there are many ways in which you can look at that. One way is we are trying to sequence the genome of the bacterium and then compare that genome with genomes of bacteria from related groups that are actually active nowadays. So we can try to see whether we see something like a signal of a very old DNA being contained or very old functions being contained, but that's something that we will do in the coming months. The other point concerning are they from the well or from the surface, the fact that they don't grow at room temperature is somehow also reassuring in our sense. If they were growing like crazy at 20 degrees, 37 degrees, then you will be a bit more quasi about, okay, is it something that we put in when we were sampling? As Simona said, we try to be as careful as possible to make sure that what we are analyzing comes from the wells. I hope that that answers some of the questions.
Yes, I think that's good. Thanks a lot. So this was actually maybe a short introduction. Pilar, she's the professor at the University of Neuchâtel working with us in the REFLECT project, obviously on the microbiology. Then I have a next questions. Did you already identify different kind of bacteria depending on pressure temperature conditions, or are all the same?
Shall I continue?
Yes, please. Good to have you here, Pilar.
So, but Dana can also help. So Dana is actually the PhD student doing the work. So I don't want to steal her thunder because it's a lot of work. So at the moment, one has to say that usually when we go to the different plants, we don't have multiple sampling sites, with exception of the work that we did recently in Iceland, where you have really different wells and you can really then compare between different pressures and temperatures. Unfortunately, in the case of Insheim, we have only one production and one injection well. So we are at this point not correlating this with temperature and pressure, but we will do that at the end of REFLECT when we are able to compare the results from different plants. So one has to say that this is one of the plants that we are working on, but we have multiple examples. So we are hoping to be able to achieve that once we get all the data.
Okay, and then I have another question for you. In how long time period can these microorganisms cause clogging effect within the well? So that's more on the influence of those microbes.
So we are investigating that together with TNO. So at the moment, what we are doing is taking advantage of these cultures that we have obtained from some of the samplings, and we are preparing samples for TNO. So we are coating still materials with these bacteria, so creating somehow biofilms with these bacteria and fungi. And the idea is to send that to TNO. They will get those samples and then test the ability of these organisms to induce clogging or to induce mineral precipitation. So we hope to get also this data in the coming months after just being able to partner up with other people from the REFLECT project.
Okay, excellent. And then there's a last one, again to Pilar, relatively to the bacteria. You just stated they don't grow at room temperature. Does this mean they do not grow? So no grow or very slow grow?
No, they don't grow. So it is really as Simona presented. What we do after we isolate them is we test all the different conditions, temperature, mainly here in the lab, mainly temperature, salinity, and different nutrients in which they grow, and in under 30 degrees they don't grow at all. So you can have these plates basically clean forever. And it's the same when Simona mentioned these Vinogradsky columns. We also prepared some that were put at room temperature, and those never actually show any growth. So everything that we have seen associated to geothermal stations always grows above 60 degrees in general. So it develops above 60 degrees. So not at room temperature, you have nothing. Your medium remains clean as long as you want.
Okay. Thanks a lot, Pilar. I think the next one is more general. So the Pfalz is known for its onshore oil fields. Did the study encounter any organic fluids, methane or higher? And then there's actually a second question, also at Sulz, radioactive minerals cause scaling. Any seen here? So these are two in one.
Yes, so I can try in this case. So concerning the organics in the dissolved phase, there is very little. So on the organic, what we've seen, and these are only these low molecular weight neutrals, so no complicated carbohydrates. In the gas phase, as far as I know, there is also little methane, but I should maybe check that again. Give me a second to go into the template. The other questions on the radioactivity. So there is the methane content is 2.2 volume %. So most of the gases is actually CO2 here. So it's not really related to gas fields, I'd say. Concerning radioactivity, yes, they have, like most of the geothermal sites that go to greater depths and that suffer scalings from barite or lead, there's always some radioactivity in there. That's why you have to be careful with the scales and put them on a special waste depository. So this is something that is not in a range where it's really dangerous also, but it has to be considered and handled carefully.
Okay, thanks a lot. I think these were all questions for the moment, and therefore I would like to move forward to the next presentation. Thanks a lot again, Simona, for the nice presentation, and also to Pilar for answering the questions. I have now the pleasure to introduce Joerg Uhde, the CEO of Pfalzwerke Geofuture, which is a company who owns and operates the geothermal power plant in Insheim in southwest Germany. Joerg Uhde holds a master's degree in mining engineering, and he has a wide background in geothermal projects in Germany as well as Switzerland. He was the head of the Department of Geothermal Power Plants for Axpo Power AG, and which is the dominant energy provider in Switzerland. Prior to this assignment with Axpo, he predominantly was involved in the field of geothermal probe drilling and the development of deep drilling technologies. At his present position, he focuses on optimizing the thermal water circuit by solving scaling and corrosion effects. He's very open towards new research ideas and also to participation in national and international research projects, especially by providing access for researchers to the geothermal power plant and also to the connected data. We in the Reflect project are very happy to have Pfalzwerke Geofuture and Joerg Uhde and his team as a partner in the Reflect project. And with this, I would like to hand over to Joerg, who first presents on efficiency in geothermal power plants and then will give us a virtual visit to the Insheim geothermal power plant.
Thank you so much, Katrin, for this nice introduction. I feel very honored. I think we both are quite happy about this cooperation we have on the platform of Reflect. As not only the scientific side will benefit from having access to an operating site, but as well, it's a win-win situation as we learn a lot from the outcomes of Reflect. We already have learned a lot, and I'm very positive that there will be further very fascinating results, which will help us to optimize our brine water circuit a little bit more. So a warm welcome to everybody. I'm very happy that I'm allowed to show you a little bit about our geothermal power plant in Insheim, and I would like to start with a short presentation to give us some background information of what it's about. And I will just jump in the side. This is a bird's view from which you can see on my backside as well, how the small power plant is wonderfully embedded in the southwestern wine region from southern Palatina. So we do not only produce renewable energy as well, we are very capable in producing excellent wines. And for those who will find time to come by personally, there will be always a very excellent dry Riesling label from our company for you. Well, not only the site Insheim itself, but I'm very happy that we have a very fascinating activity, which is shown in this spreadsheet actually in our particular geothermal area in the Rhinegraben, which stretches in the upper Rhine Valley from northern France to Germany. And the sites shown above, highlighted in green, are the already existing sites. Of course, everybody will know about the world-famous R&D site, Sud-Forêt, which is roughly 45 minutes from our site and found away. A very interesting plant as well as the Rittershofen heat-providing plant for industrial park close to the Rhine. Our predecessor at the Landau geothermal power plant, which is just 6 kilometers away from us and will be extended by drilling a third well to solve an operating problem which I have right from the beginning, as I have a very low permeability on the reinjection side, and we do hope very much that they will be able to increase the flow rate, and by this also to increase the power output. Well, as well, the further existing geothermal sites on the German side are, of course, our Insheim geothermal site, and a smaller one on the other side of the River Rhine is the Brussels site, which is operated by the large utility company Energy Baden-Württemberg, which has been developed to an R&D site, and I will later come back to this, where they actually have a very interesting R&D project in operation to extract lithium out of the geothermal brines, and all the other ones who will later look when my presentation will be shared. So a lot of projects are under development. Just to mention number 10, for example, this is a private investor, the German Geothermal or Deutsche Erdwärme GmbH, very serious back finance from a large Danish pension fund developer, Copenhagen Infrastructure, and they have a very interesting, fascinating pipeline under development. Not only these 3 sites shown here, but further ones will come and will be published later on. And we really do hope that this will have a positive impact on the development of geothermal energy in the Upper Rhinegraben. Very well known should be Vulcan Energy, a company which intends to extract lithium out of geothermal brines, just starting to start their first projects, but it will take a while until they will be under operation. In France, unfortunately, beginning with under 17, we have a backfall of the geothermal development caused by the Vendenheim project, which has been started with very much hope, but they didn't succeed in establishing a functioning brine circuit, as the reservoir is more or less tight. They could not realize very productive wells, and especially the reinjection site has a very low permeability. Therefore, by testing the brine circuit, they re-injected with wellhead pressures up to 100 bars, thus causing severe induced seismicity, and therefore the project has been suspended by the local mining authorities. And therefore, actually, not much is going on in the northern Alsace region, but I do hope that there will be a change in early next year. Well, what is typical for the Rhinegraben, Simona already showed, we have a very high salinity. The average temperature of the produced brines is around 170 degrees Celsius. We have a temperature spread of around 100 Kelvin, so the reinjection temperatures differ from 60 to 80 degrees Celsius. I will later come back on this as it is depending from the ambient temperature. The operating pressure on the above brine circuit should be above 20 bars on the production side, so on the hot side, just to keep non-condensable gases within the brine. And the average flow rate overall existing well is around 70 liters per second. So we explore the deeper upper Rhine graben at exploration or drill depth up between 4 and 5 kilometers. As Simona already mentioned, our wells have a TVD, true vertical depth, of around 3,800 meters as they are deviated, so the measured depth is roughly 300 meters longer. On the western side of the Rheingraben, we explored the upper basement, so the fractured granite in the basement, and as one source of our brine. But the more productive geological layers are, of course, the Triassic and especially the Bund sandstone, upper Bund sandstone. On the eastern side of the Rheingraben, there we have a difference in the depth of the layers, and the projects being developed over there will drill only in the sedimentary layers, so they will not reach the fractured basement, which is due to a major fear for reduced seismicity, actually not allowed by the mining authorities in the state of Baden-Württemberg. So coming back to Insheim, this is a short overview about the project history. Just to keep it short, the project has been started with the first idea in 2004 and went on to operation 8 years later in 2012. In between, of course, an exploration phase has been executed. Then the first well, our present reinjection well, has been successfully drilled. And after these results, our present owner, the Pfalzwerke Group, bought the development company via a share deal and developed the project further with the same team before. The second well, our present production well, has been successfully drilled, and after a very intensive test phase, it has been found out that the probability in the previously drilled first well was not sufficient. Therefore, a sidetrack was drilled in the first well. This helps quite a lot to reinject our brine without any additional pumping power, and we have a very low reinjection pressure above ground. And then the power plant went to operation in November 2012. So a year from now, we will have our 10th anniversary, and I presume that there will be a wonderful party on site where you all, of course, are invited to. So Simona already showed our typical technical data. So the brine temperature is around 165 degrees Celsius. Due to not very promising reservoir situation, we cannot reach the intended 80 liters per second, which was the design base for the whole project. So we operate actually between 65 to 70 liters per second. By this, we will be able to generate 4 megawatts of electricity, but grace to a very high availability. The annual output is around 28 gigawatt hours of electricity. Actually, there is no thermal output, but a project for providing heat for a greenhouse is under development, and probably with the support of another Horizon 2020 project called GeoPro, we will be able to realize this project in due time. As all binary geothermal power plants exploring deep reservoirs, we have a fairly high on-site power demand of roughly 20 to 25% of the produced electricity. The financial basis for all these projects in Germany is the remuneration under the German Renewable Energy Law or Act, which guarantees a funding of 25 euro cents per kilowatt hour electricity for a period of 20 years. By this project, which will have an investment of 10 years ago of around 50 million euros, nowadays it would be 10 million euros more expensive, can be back financed by this funding scheme. So as you know, we have two different circuits operating in a binary power plant. And in the background, we have this closed circle, our brine circle, when we're producing the brine at 165 degrees Celsius and 20 bars on the production side. We extract heat out of the brine in a group of heat exchangers. We will later see more in detail, transfer the extracted heat to a second closed circuit, the so-called organic Rankine circle, which in our case is operated with the working fluid isopentane. This will be vaporized in a vapor group of heat exchangers and vaporizes, thus driving a turbine, which is directly connected with a generator. And after, when the vaporized isopentane will expand in the turbine, it then has to be condensed into a complete fluid condition in a large air-cooled condenser, and then the whole circuits will start again. So the reservoir development is shown here. We drilled two wells, as already mentioned, the production well on this direction, and later the reinjection well with the sidetrack shown here. And we reached traces of faults, which are shown here, and not only in 2,300 meters depth, but as well, of course, in the top basement as well. This is another picture of the reservoir model, which has been designed before drilling the wells. And the major advantage is the sidetrack in our injection well. And actually, we are planning under a German funding regime an interesting project for the near future to drill also a sidetrack on our production site, with the major idea behind that, not only to enhance the productivity of the overall site, but as well to show that it's possible to enhance the flow rate in an existing geothermal system by mitigating induced seismicity. And we are quite sure that will be possible. Well, but coming back to this induced seismicity, due to the general geological situation on the upper Rhinegraben, which is still under development, we are forced to operate two independent seismic survey networks. The stations shown in red are standard seismic stations, which are placed out in the area around our site. That was shown here, and the landing points of our wells, the reinjection well, and this is the production site. But as well, we are operating an independent network of ground velocity sensors, shown with these blue dots. And the outcomes of these ground velocity sensors are important for us, as we have to respect this traffic light system to handle our induced seismicity, which is sectored in 6 levels. And by a very reasonable operation of the site, we are able to always operate our site in the level 1, which is our standard operational range. So therefore, we do not affect higher levels of induced seismicity, and therefore we were able to gain a very sufficient public acceptance by our site. And what is interesting as well, so this is a sketch from our seismic survey team, which is independent from us. Most of these events occur on the production sites, and a very slow and a small number of events only occur on the reinjection side. This is once again show the result of this more or less ideal situation by having a sidetrack on the reinjection side, realizing a very nice permeability on the reinjection side. But as already mentioned, as already has been asked in the Q&A sections, we have to face some operational challenges by operating a binary geothermal power plant. This is, of course, a very top issue is well integrity. So to prove the integrity of our wells, this is a very strong demand of the mining authority. Then to operate and manage our production pump, I will come back to that later. And as well as Simona already mentioned, of course, we have to deal with these technical enhanced natural occurring radioactive materials, so-called TNOM, which occur by scaling out in our heat exchangers, vaporizers, and other sides of the the brine circuit as well. Due to the high salinity, we have to respect brine-induced corrosion, and I will later come back to that, effects of climate change. So this is a small photo showing an intensive logging in our reinjection well to produce data for developing a concept for proving our well integrity, which was successfully finished later last year. And actually, we are preparing the well integrity proof for our production well in combination with an exchangeable production well next year. This is the system of our production pump. Due to the fairly high brine temperature of more than 50 degrees Celsius, this usually used electric submersible pumps, which are the standard technology in the Bavarian Molasse Basin and other geothermal sites in Germany and elsewhere, especially in France, for example. We have to use so-called line shaft pumps, which have been developed on the basis of an existing technology from the oil industry. They just have to be evaluated for a fairly higher flow rate, which is 10 times as much as it usually occurs in an oil well. And therefore, we have a 39-stage circulation well divided in 2 sections only for transport reasons, which is installed in the pump chamber in our production well at around 750 meters depth below surface. And this circular pump is driven by a line shaft, as the driving motor is placed above ground. And you may imagine it is more or less complicated to deinstall and reinstall this system into an existing well. And here you can see the extracted pump, quite a long tool with the connection box right in the middle, which is just ready for being installed into the well. And this operation will be repeated next year, as we have a slight design failure in this particular toolbox. Therefore, the pump has to be extracted and will be changed by another pump. Then when restarting the power plant, of course, we have to heat up the whole brine system, especially the production pump in our well, and therefore for a limited period of time over 1 day, for a reason normally we have to operate the brine circuit over this here shown separator, and then we have a wonderful steam phase above our power plant. And it's always quite tricky to adjust the driving shaft of this production well pump. As you may imagine, when it's 750 meters long, it will extract by being heated up, and therefore it has to be readjusted 2 or 3 times through the restarting procedure. T-norm, of course, is a result of scales occurring by changing temperature and pressure, or maybe both, in our heat exchangers. And the main source for this T-norm is the isotope lead-210, which scales out maybe usually together with barium sulfate. So we have to minimize these effects by using particular inhibitors. Simona already mentioned that we are quite successfully so far, but the outcomes of Reflect will definitely help us to optimize the system later on. This is how the open heat exchanger, or this is the vaporizer, looks like. And within these vaporizer or heat exchanger tubes, with a length of roughly 25 meters and a diameter of 1 inch, there we have the scaling effects, and these tubes have to be cleaned every 2nd year. And the cleaning residues then are these T-norm residues or scales. And there is no disposing of solution in Germany for the cleaning residues, as they occur directly after the cleaning process. They look like this. So we have to treat them on site by immobilizing this and adding special additives like iron oxide and special cement, and then to transfer it in a disposable format, which is shown in the brown version on the red side. But the idea actually is to develop a solution that we will be able to treat these residues in a certain way, and then we return them back with a returning brine fluid into the reservoir. As well, we have to face corrosion effects. By this, we exchange standard steel pipes by fiberglass reinformed pipe sections, but this is of course due to temperature effects only possible on the low temperature section of our brine circuit. So we have already mentioned, and the question already occurred, we have a very high content of non-viscous condensable gases, which is mainly carbon dioxide, shown here for different sites in the upper Rhinegraben from Insheim, Sulz, and Potsdam. And we have very low contents of organic gases. And so the methane is already a content between 1 and 2%, and we have a little bit nitrogen. So the major advantage of this high carbon dioxide content is that we are able to work on the open wellheads without having any HSE issues in combination to this. But on the other hand, of course, we have to operate the whole brine system above the degassing pressure bar, which is between 19 and 20 bars different from different sites, to keep the carbon dioxide within the brine. And here you can see the difference of the degassing temperatures. And of course, as you know, by cooling down the gas, the brine temperature, the degassing temperature is lowered, and the degassing pressure is lowered, and then we are able to reduce the operating pressure in that circuit. As well, it's already mentioned, of course, we do have understood that this is very helpful for us to be part in several R&D projects, to have an exchange with the scientific community. And as well, I feel we are obliged to do so, as by the end we are a funded project, and we should give something back from our learnings, which we have realized by operating the power plant over a certain period of time back to society and to the scientific community. And I'm very happy to mention as well, of course, it's enrichment for all of us, as we profit very much from that. And by the end, it's just a lot of fun to have this exchange of know-how with the esteemed scientists. Well, lithium is actually a very high topic in the media, as we have an interesting lithium content in our brine, which differs in the upper Rhinegraben between 170 to nearly 200 milligrams per liter, and therefore the idea popped up whether it would be possible to extract lithium out of operating geothermal brine circuits. So a site in the like Insheim, for example, would be able to produce, once a technology is available, which has not been definitely developed so far, could be able to produce around 700 kilogram of lithium chloride, which is roughly 1,000 to 1,200, 700 tons, I'm sorry, 1,000 to 1,200 tons of lithium carbonate equivalent, which is basically lithium hydroxide, could be generated per geothermal site. This is an interesting number, could be added value to the operational site, but by these small amounts overall, we will not be the game changer for the lithium market worldwide. So now I will shift over to visit virtually our geothermal power plant. This is a bird's view showing you the main elements of our power plant from bottom to top. This is our production well, the injection well. The production well, we will start our virtual tour. This is the grid connection where we have our transformators. There we have our control system. There we have a thermal water treatment. We already have seen some pictures from inside in Simona's presentation. And under this roof, we have the power production facility, the heat exchanger, the turbine. And this is the largest element of our plant, is the air-cooled condenser, where we condense the working fluid of isopentane. Just please allow me to switch to another screen, and then I'll be back right away. So now welcome. My screen is visible. I hope so.
Yes, fine.
Okay, perfect. So we will start our tour on top of our, sorry, this is not, on top of our production pump. And this is the driving shaft of our production pump, which is led through our driving motor. And in this section, we adjust the whole driving shaft when bringing the system again in operation. So now we will start right here to give you an overview how this operating system looks like. This is the driving motor for our line shaft pump, and the hot brine is pumped in these isolated pipes passing by a service station. There we have installed a cooling tank as the bearings in the motor and of the driving shaft for our pump are water cooled, and as well we have a greasing system as the driving shaft is rotating in a so-called loop string, and we continuously pumping a certain grease into that loop string. The demand is roughly 1 oil drum per week, and but this will be retreated twice a year by reactivating the well, so we do not spend oil in the reservoir. And from here, the brine is pumped into our heat exchangers, where we now will directly go to. This is the group of our heat exchanger. The hot brine is coming through this isolated pipe, entering our vaporizer on top. This is the hottest point of the heat exchanging system, and then flowing out of the heat exchanger through 2 preheaters, and then flowing back into the brine treatment facility and back to the reinjection well. And the working fluid in our OSC unit, this isopentane, is flowing through this line into the upper colder preheater. There we have the most scalings, and this is the coldest point of the heat exchanger system, and then flowing from this into the second lower, even warmer heat exchanger, and then entering in the bottom, the vaporizer, where it will be fully vaporized. And from there, it will stream over as a vapor to our turbine, which we will see from the other side, where we have a better view from there. And this is the vaporizer. On top, we have a so-called demister, which takes care for that we do not have any fluid drops in the vapor, and this would have a negative impact on the turbine. So the isopentane vapor is flowing on top into our turbine, is rotating the turbine. The turbine is directly connected with the generator, we can see right in front of us, and then expanding out of the turbine in a horizontal way to the left side, and from there flowing through this large horizontal distribution pipe, and then streaming through this large condenser, which is more or less working like a cooler in your car, which you're operating, where we have these large fans on top, and we are just having the air streaming from bottom to the top, and by this cooling down the isopentane, and when it cool down, it will condensate again. And on the other side, which we'll later see, we have a so-called brine pump, or not the isopentane pump, sorry, it's not the brine pump. And this isopentane, then when it's already as a fluid, then it will be pumped back into our heat exchangers. But what is more important for us to have a look back into our brine treatment facility is, due to our very high mineralization, we have to take care that we have a proper operation of our brine. So the hot brine is coming by this pipe directly from our production well. Then we have a filter section with 2 parallel filters with baskets with a measure of 150 microns. These filters are permanently in operation, but have to be maintained only after a restart, after a longer maintenance shutdown. Then we will have mobilization of fines, but as well scalings, which occur by restarting the pump. And we got some interesting learnings as we reactivated the system after we had our annual maintenance shutdown in late summer this year, and we wanted to restart our brine pump. After the first start, the pump shut down and it was not possible to rotate it anymore. And together with several consultants from all over the world, we tried to find out what might have happened. And by the end, we found out that just by differing or changing the pressure in the brine system, by starting and then stopping the pump, as we had to readjust it. So we have a change in brine pressure, and then we have had a scaling effect. And we had a lot of calcite scalings, which we fortunately found after the first short test in our filters. And we had an analysis of these scalings were more than 99% of calcites, and we assumed that these calcites might have scaled out in the pump stages as well. And by then the idea was to have an acidation drop and just to acidate these calcites in the pump. And it was a very well, it was a very stressful situation, to be honest, but by the end, this acidation drop ended up successfully, and we were able to restart the pump. And since then, it works very sufficiently. So then after these filters, the brine is passing by at two inhibitor stations. This one is organic acid preventing barium sulfide from scaling out in our brine. This is very important, as I already mentioned. The radioactive isotope lead-210 precipitates in combination with barium sulfide. So when we are able to reduce the amount of precipitating barium sulfide, by this we just automatically reduce as well the T-norm storing. And the second inhibitor we're actually using is a combination of a corrosion protection fluid, which sets up a corrosion protection film within our piping system, and as well is helping to reduce further precipitation effects as well. So then the hot brine is then entering the vaporizer we have already seen outside. The cooled brine is returning through the already shown plastic pipe, and then will be filtered again on this side. There we have more filter stations. We have 4 filters, 2 double filter stations frequently have to be maintained as by cooling down the brine in the heat exchanger group, and by this also changing the brine pressure. We have these precipitation effects, and we want to prevent these scalings from our reinjection well. So from here, we will have a short look in our storage hall. So when our power plant was designed, of course, the designers had learnings from the Landau power plant, and I informed you earlier that Landau is suffering from very low permeability on the reinjection side. They can only reinject the brine by using a reinjection pump, and so the designers thought it might be possible, might be necessary on our side as well. So right from the beginning, 2 large reinjection pumps were planned and finally installed as well. But they have never been in use, grace to the fact that we have this later drilled sidetrack in our reinjection well. Therefore, we have a very low reinjection wellhead pressure, grace to this excellent permeability on the reinjection side. And so these very much power consuming reinjection pumps have fortunately not been in use so far. And I hope this will not change. As well, we have a small control room. As we always have to keep in mind, this is a design stage 10 years from now, or maybe even 12 years from now. Probably today, a more modern designed power plant would have looked a little bit more fascinating. So we are operating 2 different control systems. The brine circuit has a different control system working on a Siemens S7 system, and the RRC unit, turnkey delivered from an Israeli provider, the world-leading Ormet Group, has another control system, an American control system from Allen Bradley, but they are connected together due to security reasons or safety reasons. And we are very happy with this solution. It works pretty well. Usually we have 3 to 4 people on site when we have regular working hours. We have, of course, a regulation. We have daily controls of the whole system to assure that everything is in order. And we have always one colleague on duty, changing every week. So if we have an alarm on our side, so it doesn't take more than much more than 20 minutes to be on site and then to keep everything fixed. Fortunately, this doesn't happen very much often. But it is as well quite interesting, even for our R&D project, where we are happy to be involved in, that we have collected a lot of data, especially from the brine circuit, not only the water level, the brine pressure and everything else. And all these are stored in this data collecting system, and they can be made available, of course, for any scientific projects. And actually, it's quite interesting to find an algorithm and a combination. Is there a combination between occurring induced seismicity and changes in operational procedures for the brine circuit? It's not proven yet, but we have an idea that it will be possible to show this. Now let's have a look back from top of our condenser. Have a nice view back into our wonderful wine region. So once again, whenever you find time to stop by, just let me know, and we will be happy to welcome you on our site, to have a direct walk through our site, and to give you an impression how a very small geothermal power plant is operated as well. So once again, having a look through our 2 wellheads. This is the reinjection wellhead, this is the production wellhead. And what helped to keep a former mud pit from the drilling phase, which has been enhanced as a storage basin for our brine. This helps quite a lot in the operation when we have to restart the system and can temporarily store all the brine over there. And now I turn back that you have a look at this large group of fans, which we continuously operate to condensate our isopentane. Thank you very much for your interest.
Thank you very much, Joerg, for this very nice presentation and the virtual visit. We actually have a lot of questions already, so you're not yet done. And I directly start with the first question. Do you know if some of the induced seismicity is due to different brine temperatures around the injection well?
So far not as, yes, oh well, maybe it could be. So let's switch over again to the screen, and then it's a good example. So you may imagine that the efficiency of our condenser depends on the ambient temperature. As the cooler the ambient temperature will be, the higher will be the efficiency of our condenser. And the other way around, the warmer it becomes in the summer times, the efficiency is lower. By this, we have to reduce the flow rate, and the returning temperature on the top of our reinjection well is rising in very hot summer days up to 75 to 80 degrees. And then, of course, the question is excellent. We measure an increase in induced seismicity on the reinjection side.
Okay. Interesting.
Mm-hmm.
Then we have the next question. You have to pump water from the production well. What is the level of water? DH.
The actual level of water in the operational site is about 450 meters below surface.
Okay, thanks. Then another question on the seismicity. What is the progress on flow rates, pressures used to keep the level of induced seismicity event or induced seismic events below the felt levels for the local population?
Well, we can assure this by ramping down and ramping up the flow rate before an intended shutdown of the unit. So, for example, we have a planned maintenance shutdown as we do it for preventive maintenance in our power plant. Then we will reduce the flow rate for a period of around 2 or 3 weeks. And when restarting after a longer shutdown, as we unfortunately have had due to this mentioned pump issue in the summer, so the restarting period will take about 6 weeks. And by this, we are able to keep the induced seismicity very well controlled.
Thanks a lot. Then we have a question towards, what is the lifetime or life expectancy of a doublet system under current production conditions?
Well, a well should be well designed for a very long period of time. So at least, from my personal opinion, of at least 50 years. 10 years ago, probably the idea of these design phases was a little bit different, but we are able to keep our wells in a very good shape. And therefore, I'm very positive that there will be a safe operational period of up to 40, maybe even 50 years. And as well, the above ground installations will allow a very long operational period as well. As of course, you may assume that the whole project is calculated for a duration time of 20 years, and this is the basic funding period we profit actually from. But we have to keep in mind, even on the last day of this 20 years period, the whole system has to be in the same excellent shape as it actually is.
Yeah. Did you actually already see some temperature changes in the reservoir?
No, we don't.
No. Excellent. There's a more general question towards what you showed at the very beginning. The projects planned by Vulcan, are they economically based on lithium extraction? What about lithium extraction with adionics?
We are well connected to adionics, know them quite well. Adionics is a startup from France, and they developed a very selective lithium extraction process, which is basically focused on the brines from the lithium triangle in South America. As far as I'm informed, their process does not allow an operational temperature of more than 40 degrees Celsius. So this has to be tested whenever it will be of interest for adionics, whether it will be will allow higher temperatures, or once we will be able to extract further heat for a potential greenhouse, then of course we will have lower returning temperatures, and then maybe it will fit. Okay.
Mm-hmm. And the question towards Vulcan, whether they are based on lithium extraction only?
The business case of Vulcan is a combination of geothermal power generation in combination with lithium extraction.
Yeah. Okay. Then we have a question towards the fans, which you are still showing. How noisy is a power plant? Is the air cooler the most noisy part?
Well, actually, as you can see in the background, we have a noise pretension wall built there. We were obliged to build so. So when returning back, and I will just give you a bird's view of, there behind this noise pretension wall, there's a railway line. And just on the other side of our plant, there is a highway line. So actually, I'm not quite sure whether this noise protection wall protects the railway line from the noise of the highway, or it's the other way around. But besides joking, we do not have noise impacts through our vicinity, and of course you may hear them, but as the motors are regulated by changing the frequency, they are not very much noisy.
Okay, there's another question towards the plant. What is the dimension of the heat exchangers, where the ORC fluid vaporizes, and what type of heat exchangers, plate or shell and tube types? I'm not even sure if I understand the question, but maybe
let's have a look at them, but sorry, I just switched up. Something went wrong, I'm sorry. We have it, just give me a second, just jump back to the heat exchangers. There we go. So we have tube and shell heat exchangers, and for example, in our vaporizer, we have roughly 1100 tubes with 1 inch diameter. It's a special stainless steel. And these tube and shell heat exchangers allow a very excellent cleaning operation. Plate heat exchangers are definitely more effective, but it's difficult to clean them, and especially if you're operating a fluid with, as our brine, with a very high precipitation effect, then plate exchangers will not match the product of selection.
Okay, thanks a lot. I have one more question. What is the typical temperature variation of the produced thermal fluid during normal operation? Actually,
100 and 165 degrees Celsius.
Okay. And then second, what load percentage of the maximum is typical operating condition?
Don't understand this question, to be honest.
Yeah, me neither. Yeah. Yeah, I also don't know. Then we have one more question. What is the relationship with social acceptance? Is there information on seismicity induced with seminars?
No, but our seismic events are published through a platform from the mining authority in our state of Rhine-Palatina. So everybody has access to these seismic data, which occur by operating even natural, but also induced seismic events.
Okay, thanks a lot. Maybe one last question before we close. There was a question on, are there cascading utilization of brines such as direct use?
Well, as already mentioned, we are working on a project to further cascade our energy from the brines work to deliver heat for an intended greenhouse project close by.
Perfect. I think that was mostly it. There's a small question, a non-technical question, whether Joerg Baumgartner is still involved in the project. This is a question from John Helm, who visited the site in 2013.
Yes, I've just read the question. So Bestek was the designer of the project, and we operate the project until, or the site until 2019. And then we had a change in the organization, and since then Bestek is no longer operating the power plant. Okay.
I think that was all from our side. Thanks a lot, Joerg, for answering all the questions. Thanks a lot for this very interesting tool, also from the visitors who said that this was very nice and interesting. Well, we are looking forward to visiting Insheim again in the future. We are looking forward to more research jointly together with you, the Pfalzwerke, and our partners. And with that, I would like to thank you again for the webinar, the presenters. Also, thanks to Simona once more. Thank you for all the visitors and listeners. And I would like to remind you that the webinar was recorded. Whenever you want, you can have another look on YouTube.
Thank you very much
for joining us.
To participate, and a very warm goodbye to all the interests. Bye-bye.
Thank you.
Bye.
Bye-bye.
Bye.